All right, so chapter 6 is a lot shorter than chapter 5 because we're mainly just going over two big ideas. One, discrete probability distributions, so talking about the difference in discrete and continuous variables and stuff again like we did back in chapter 1. And then specifically looking at the discrete probability distribution for the binomial. And so those are the two things that we'll be talking about in this chapter. And for the most part, we're going to see how we can do it all in our calculator and not so worry so much about all the formulas and everything that we could use, but we're, going to use technology in some way. So chapter 6, discrete probability distributions is the name of this one. So 6.1 is just looking at discrete probability or discrete random variables. So interpreting those like we did back in chapter 1. A random variable, though, we haven't necessarily talked about that, but a random variable is a quantitative variable whose value depends on chance. It's a variable that assumes numerical values, of course, because it's quantitative, right? Associated with the random outcomes of an experiment denoted using capital letters such as capital X. So when flipping a coin, if the random variable X represents the number of heads and 2 flips of a coin, the possible values for X are 0, 1, and 2. Right? So the random variable is just, what we're interested in recording or finding information about. So in this case, it could be the number of heads. It could be the number of times you roll a 2. It could be how many males you get in your group if you're randomly choosing a group, something like that. Those would all be random variables. So we've already been dealing with those in chapter 5. We just didn't necessarily call them random variables. But then talking about the different types of random variables, just like with just general variables, we have discrete and continuous random variables. So discrete random variables are a random variable whose possible values can be listed. It's usually a count of something, so you may remember that back from chapter 1. Discrete variables are when we're counting something, we're able to list the entire, like sample space. If you want to think of it that way, we could list all those possibilities if we wanted to. A continuous random variable is something that could be decimals, fractions, anything on the number line. You're typically going to represent it more as like X is greater than 0 instead of saying X is going to be 0, 1, 2, or 3. So it's more broad. When we talk about continuous random variables, they're usually going to be like measurements of something. So height, weight, time, all those things would be continuous random variables. And that's what we'll see more of in chapter 7. So let's just identify these as continuous or discrete, and just kind of reminding ourselves of what we did back in chapter 1. So how many people in a sample would say vaccines should be mandatory for students? So what would that be, discrete or continuous? Discrete, right? Because we're going to count how many people would say yes or no, looking at it. The length of time in seconds between arrivals at a hospital clinic. So what would that be? This would be continuous because it would be something you're measuring. You're not really going to be able to list all the possible outcomes of something like that. I mean, you could say that it's going to be greater than 0, right? But you don't necessarily know all the possible values that you could get with the length of time between hospital arrivals. And then the last one, the number of customers waiting to be served in a restaurant. That would be discrete, right? Again, you've been counting how many there are. So discrete are typically going to be whole numbers. Continuous can kind of be anything on the number line. So if you need some more examples of that, there should be some in the homework. But also you can go back to chapter 1 and kind of refresh on some of those discrete and continuous examples we had back there. All right, so the probability distribution of a discrete random variable. We looked at probability distributions already. What they do is they list out all the possible outcomes for X and then the probabilities that go along with each of those outcomes. We said that all those probabilities should be between 0 and 1, right? And then they all should add up to 1. And that tells us that all the events were listed that we needed to have, that we didn't double count anything or forget forget any of the events. And so like it says here, they should all add to 1, just like we saw in Chapter 5. So let's say that this probability table or distribution is representing the number of surgeries on a given day for a local plastic surgeon, and we have the probability for each of those. So this would be calculated using relative frequency, so empirical probability, right? Maybe they look over the last year or 2 years or 3 years or whatever and saw, how many days were there 3 surgeries, how many days were there 6 surgeries, right? And they just looked at those percentages to then predict, this is the probability that a certain day would have a certain number of surgeries. So the random variable for this one, so when we're trying to find what the random variable is, you can look at, well, what does X represent, right? If I say X is 2, what does that mean, right? And so for this one, an X of 2 would mean they had 2 surgeries scheduled that day, right? So the random variable is the number of scheduled surgeries per given day. So something like that. We're looking at the number of scheduled surgeries on any given day. So what's the probability of 2 surgeries? We can look at that chart and find that. So is this variable going to be discrete? Yes, right, because we're counting the number of surgeries, so we would say yes. What is the probability that on a random day the surgeon would have 4 surgeries? So to write this out, we could write it like this, right? Because X is our random variable, so we're wanting to know the probability that our random variable is equal to 4. You also could just write it like this. These are the same thing, so just different notations, so those are the same thing, just however you want to kind of write it out. You could write out the probability and then there write 4 surgeries per day or something, right? You could write out a whole sentence in there if you wanted to, but you're probably going to see it one of these 2 ways. With the homework. So the probability that we would have 4 surgeries on a given day, it would just be 0.10 or 10%, right? A 10% chance of that happening. So there we're just reading the chart, okay? So the chart's already been given to us, so we're just reading it. If we had like the original data, maybe we were creating a frequency table or a relative frequency table, and then from there we could find the probability. All right, and so like on the next one, we're actually going to create that probability distribution like we see here based on classical probability of what could happen or what should happen here. So when a balanced penny is flipped 3 times, we have 8 equally likely outcomes that are possible. We are going to count the number of heads kind of as our success here. That's what our X value is going to represent. And so that means that our possible X values would be 0, 1, 2, or 3. So we can't have less than 0 heads because we're not going to have negative heads, right? And you can't have more than 3 because we're only tossing it 3 times. Okay, so one way to figure out that we would have 8 equally likely outcomes is to, draw out the actual process of all our possibilities, which we would call a decision tree like this. Or we could say, this is the first flip, this is the second, and this is the third. Right? And then we see, well, these are all our possibilities. So there's 1, 2, 3, 4, 5, 6, 7, 8. Right? We could do that. The other thing we could do now, since we know about the multiplication rule of counting that we did at the end of last chapter, we could just say, well, there's 2 ways for the first flip, 2 for the second, and 2 for the third. So that would also give us 8. Right? So you could do that as well. This one becomes total that is 8, right? But if we had to get that ourselves, that would be how you would do that. You're just multiplying how many possible outcomes there are for each of the flips. So 2 times 2 times 2 would give 8. All right, so the first part wants us to construct the probability distribution of X. So we're wanting to see, what are all the possible outcomes for X, and then what are the probabilities for each of them. right, so the possible outcomes are 0 through 3. I already said that in the prompt there, but that's because we can either have 0 heads, 1, 2, or 3 when we flip a coin 3 times. And then how this is helpful to us is if you can't kind of visualize it in your mind, how many heads or tails there could be, this might help you to see it. You know, okay, well here I would have 3 heads, or here I would have 2 heads and a tail, or whatever. So how many times, looking at, you know, these different patterns here, how many times did we get 0 heads? Once, right? And so that would be down here. And that would be when you get tails and then tails and then tails, right? So that would happen 1 out of 8 times. So just like we would do classical probability with our sample spaces, right? So the sample space of getting 0 heads would just have that 1 option in there. And then the sample space of the total experiment would have those 8 possibilities. All right, how many ways could we get just 1 head? 3. So we can see that here. It's already kind of got the numbers written out for us. But here we could get tails, tails, and heads, right? That would be 1 head. We could get tails, heads, and tails, right? Which would be 1 head. Or we could get head, tails, and tails, which would be the other one, right? So that would be 3 out of 8. What about 2? 2 heads. 3 also. So we see that here, 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 here. 3 out of 8. And then the last one, the only thing left, there's just 1 left where we could get, if we get all tails, or I'm sorry, if we get all heads, then we have 3 heads, right? So there's 1 out of 8 ways that could happen. So again, this is our classical probability. This is not what actually happens when we do the experiment. This is what should happen if you were to do this experiment. This is how likely you would be to get 0, 1, 2, or 3 heads. And then, of course, we want to make sure that that adds up to 1, which it does, right? Just to make sure we did list every possibility and that we do have all the probabilities correct. So any questions on setting that distribution up? All right, now that's the hard part. Once we have that, then we're just using the table to answer questions. So what's the probability of obtaining less than 2 heads in 3 tosses? So we have the probability that x is less than 2 is equal to the probability that x is equal to 0 plus the probability that x is equal to 1. Right? Now if it said less than or equal to 2, right, then we would include 2. This just says less than 2. So we'd just be adding those probabilities together. So 1 out of 8 plus 3 out of 8 gives us 4 out of 8, which is 50%. So there's a 50% chance we would get less than 2 heads in 3 tosses. And there's a 50% chance we would get 2 or more heads, right? That we would get 2 or 3. So here we're using 4 probabilities. We're using the special addition rule, right? So if we're looking at the probability of less than 2, that means we either got 0 or 1 heads, right? And so that's why we're doing addition there. Okay, any questions so far? All right, let's look at some other rules that we have for probability distributions like these, for our discrete probability distributions. You might want to calculate the mean and the standard deviation for a random variable or for the experiment. And so these are going to be the formulas that you would use for that. There is another way you could do it in your calculator as well, which we'll look at. But to find the mean, basically what you're doing is you're multiplying all of your possible x values times their probability and then adding all that up. Okay, and so that's what's going to give you your mean. And notice here that we use mu and sigma here. So these are our parameters because this is talking about the whole probability experiment, right? The whole random variable. So these are parameters because we're looking at that whole experiment of what should happen. So the mean, if we did it for this one, so this this was the little chart that we just created, the x's and the probabilities. To get the mean, we would just multiply all those things and then add them up, and we get 1.5 would be the mean. Okay, so our mean here is 1.5. So then we would want to know, well, how do we interpret that? Like, what does that tell us if I know that the mean of the number of heads, random variable, is 1.5? How do I interpret that? And so how we're going to interpret it is we're thinking of that as our expected value. Okay, so the expected value is sometimes also used in place of the name mean. So if we do expected value, you might see it written like this. That instead of writing it as the mean, they'll say E of x, or the expected value of x, is equal to the mean, which in this case was equal to 1.5. And so that lets us know that in a coin toss experiment, when we flip a coin 3 times, we should expect to get 1.5 heads. Okay, which making it make a little more sense with whole numbers, that's telling us we should get 1 or 2 heads. Which we probably could have figured out just by looking at the probability distribution, right? Or just from our own general knowledge, right? Common sense there. But you can see 1 or 2 is the one that's going to happen most often, right? So we get that 1.5, so we're expecting 1 or 2 heads. And then the standard deviation, obviously a little more complex to calculate, just like regular standard deviation is. But that one we'll interpret in the same way as standard deviation. Okay, so we could then use the mean and the standard deviation with things like our empirical rule to identify something that's unusual. In this case, since there's not many outcomes, really a 0 or a 3 wouldn't be that unusual. But if we were flipping a coin 10 times or something, we would start to see where, getting no heads would be very unusual, or getting 10 heads would be very unusual. And we could prove that by showing that there are more than 3 standard deviations from the mean. So the standard deviation you could think of in the same way. So these are the formulas, so yes, you could do it that way. But let's look at how we could also do it in the calculator. I know these came out kind of fuzzy. I don't really know why that happened. So we'll look at it on the actual calculator here. All right, so the way we're going to do this is we're going to input our x value and our probability value. So we're going to go to Stat and Edit. Got lots of data in here. Let me clear these out. So if you want to clear your list, remember, go up and highlight the list here and then push clear and enter, and that will take out all the numbers for you, so you don't have to go through and clear them individually. All right, so I'm going to put in just these first 2 columns here, so like the 0 through 3, and then the fractions that we have, so 0, 1, 2, and 3. And then the 1/8, 3/8. Of course, once you put them in as a fraction, it's going to convert it to the decimal for you. So that's all you need to type in. Our probability distributions are usually not real long, so we can typically type them in pretty quickly. So we could have done the same thing for the one about the number of scheduled surgeries per day. You could put that in to calculate, well, what do we expect the number of surgeries to be. But from here, we're going to do similar to what we did in Chapter 3. We'll go back to Stat and calculate. And we're still going to use the one variable stats. Okay, but in here, we are going to have a frequency list. Remember, our probabilities are like relative frequencies. So we're going to think of that list 2 as our frequency list. So to put that in there, you go to 2nd and 2, or 2nd and 3, or whichever number is your list. So it should have list 1 and then list 2 for your frequency list. And then you should get this for your output. And so really the only thing we want here is the mean and then the standard deviation the 5-number summary and all that stuff doesn't really make sense here. So you really just want the mean, which technically would be mu, not x bar, but that's just how it's notated here. And then sigma, there's the 0.866. All right, so did everybody get that if you're trying to do it? Yeah. Okay. You didn't get those numbers? Or?
No, I got lost after the. Okay.
So then go back to that. So on this one, because the but it'll look like that. And then let me see if I can get it to show that. Yeah, if you don't have the prompts, like some of the previous or older versions of the calculator, I guess, because like the ones I have look like this, it doesn't have the prompts in there, so you have to type in the numbers or your list, right? So it would come up like this if you have one of the older versions, and then you would do second 1 to tell it, okay, these are my x values, then put in a comma, and then second 2 to tell it this is my frequency list or my probabilities. Okay, and that's how you get it to do it if you have one like that. So both of those screens are on there, but it doesn't really come out real great. But that's how we could find the mean and the standard deviation without having to worry about the formula stuff. All right, any questions on doing that? Oh, so mainly what we want to think about here is that with the mean, we're going to interpret that as the expected value. So if you're working on a problem and it says, how many do you expect to get, or what's the expected number for this experiment, it's wanting you to find the mean. Okay, so expected is the same thing as the mean. So kind of put those two words together in your mind. That's what, when you see expected, you want to be thinking about, I need to calculate the mean. All right, so that was all of 5.1. 5.1 is just introducing us to these discrete probability distributions and kind of making us recognize that there is a difference in discrete and continuous ones. We're just looking at discrete here, and then we'll look at continuous ones when we come back from fall break. So the discrete random variable that we are going to talk the most about is the binomial distribution. And so the binomial distribution cannot be used always, okay? It can only be used for certain random variables that meet these conditions, okay? In general, what we usually look for with the binomial is that we're counting a certain number of successes within a certain number of trials. So like when we're flipping a coin, if we're counting how many heads we get in 10 flips, that would be binomial. How many 5s we get when we roll a die 8 times. Okay, so we're counting something that we're going to call a success, and then we have a certain number of trials. So usually if that's the case, then you can use the binomial. But the actual conditions here are, the first one is that it has to have a fixed number of observations. So you have to have somewhere in there that says, this is how many times we're flipping the coin, this is how many people we're choosing, this is how many cards we're going to get. So you have to have that because we need to know n. So n is our number of trials. Right? We talked about that before in chapter 5, that lowercase n we also knew as our sample size, which it still can be. But we can also think of it as our number of trials. So we need to have a number for that because it'll be in the formula. Number 2, for each trial there are 2 mutually exclusive outcomes, which are success or failure. So we've talked about mutually exclusive events, right? And that's when they're totally separate circles, so they don't have anything in common. So we need to be able to identify everything in this experiment as either a success or a failure. Okay? So it could be like heads or tails, right? Success or failure. 6 or not 6 when we're rolling a die. So in that case, we would say a success here is a 6, and then a failure would be everything else. So 1, 2, 3, 4, and 5 would all be failures. So it doesn't have to be just one thing in each. It's just that everything should be able to fall into the success category or the failure category. So if that's the case, if we can separate them into two distinct categories there, then the probability of success we're going to call P, just a lowercase p, and then the probability of failure is going to be 1 minus P because we're going to use the complement rule, right? So if this is not the case, that it's either here or here, then you can't do P and 1 minus P, right? Because it wouldn't work. It only works when they're totally opposite or mutually exclusive events. So P being our probability of success, we're also going to use those in the probability of failure. Here we're going to use those in the formula. Okay, so those first two are kind of the main ones. The next ones usually are going to be true, but you always just want to double check and make sure that is the case. Number 3, your observations are independent, so they're not linked in some way. So we will, like it says for 4, we will want to use replacement when we're doing the binomial, at least for small enough populations. And then constant probability of success for each observation. It doesn't change from trial to trial. So 3 and 4 are kind of similar, but basically you just want to make sure that every trial you do, your probability is staying the same and it's not based on what happened before, that nothing is affecting, that probability. So if all 4 of those things are true, then we can use this binomial probability density formula, which is called the PDF. So this is how we would calculate the probability that X is equal to a certain number of successes. Okay. So this formula tells us probability of a certain number of successes. Okay, so the probability of 2 heads and 10 tosses, or 3 heads and 5 tosses, whatever, that would be what this PDF formula would tell us. Okay, so the formula, the first thing it starts with is looking at combinations. We talked about last time combinations, right? How we would choose, well, I think it had R, but this one has choose X. But this is just another way of writing combinations. There were kind of those 2 ways it could be written in a formula. It usually is written with those parentheses. So that first part is looking at how many ways can this happen, right? So like if I'm flipping a coin, we're thinking about heads, we could say, well, heads could happen on the first flip, it could happen on the second, it could happen on the third. So it's looking at all the ways that could happen. The next thing we're looking at is the probability of success, right? This is our probability of success. And then it's raised to the power of X, which is the number of successes. So we're using the multiplication rule here, right? We're multiplying how many ways this can happen times the probability of success raised to the power of how many successes there are. Okay, so if we're looking for 2 successes, then we do the probability of success to the second power, right? Because we're multiplying it twice. If it's 3 successes, it's 3 times. So this is just looking at our multiplication rule that we've used before. And then this here is our probability of failure, which is the opposite of success. And then n minus x is just your number of failures. Okay, so all of this really is just following what we would have done in the last chapter, using the multiplication rule or looking at how many ways something can happen. But instead of having to wonder every time we look at an experiment, like, okay, well, do I need to add stuff here or multiply, or do I need to worry about combinations, etc., we just go straight to this formula and say, okay, this is how we find the probability if it's a binomial random variable. Okay? So we don't have to wonder how to do that. Okay, we can just go straight to this formula. Okay, so that's one nice thing about identifying what type of discrete random variable you have, is that once you know which one it is, then you can go straight to the probability formula and use that. The other thing is that calculating the mean and the standard deviation is easier. Okay, so of course I just showed you how to do it before with the mean and standard deviation, but we had to have the whole probability distribution, right? We had to have all the x's and all the probability of x's. But if we know that we have a binomial random variable, I'm going to skip a slide because I'm in the middle of talking about it, but if we know we have a binomial random variable, then we can calculate the mean or the expected value by just doing n times p. So all we have to know is how many trials do we have and what's our probability of success. So we don't have to have the whole distribution written out. We just have to know those two things. And the same thing for the standard deviation. We just need to know n and p. Okay? And that will give us our mean and standard deviation. So that's a lot easier than doing it the way we saw in the first section. So you could still do it that way, the same way we saw in the first section, but if you can identify that it's binomial, then you can go straight to just using these formulas. All right, so let's go back to the other page that I forgot that I had in here. The very first step we would do, of course, is figure out, well, is this binomial or not? If it is binomial, then great, we can use all these formulas. But if it's not, then there's a lot of other discrete random variable distributions we could use, but we only really have time to talk about this one, but there are other ones. So it's not either binomial or nothing. There's other ones we just don't have time to get to the other ones. So the first one is students given a test and told to randomly guess at 30 true-false questions. We want to calculate the probabilities that the student gets a certain number of the questions correct. So to figure out if this is, binomial random variable or not, we want to look at, do we have a certain number of trials? So is there a certain number of questions that we're, yes, right? So this one has 30. So we basically be looking at each of those 30 questions as a trial and saying, did they get it right or wrong? Okay, can we label everything here, our outcomes, as either a success or a failure? Yes, right, because it says we want to look at how many he got correct, or she, whatever. And so in this case, a success would be that they got it correct, and a failure would be that they got it incorrect. All right, and then from there, we just have to make sure that, everything would be independent, that you have constant probability of success, and all that should be the case, as long as, we didn't set up the test in some way that, we made the first 10 questions true and 3 false or something. But we would assume that in this one, that it's all going to be independent, constant probability and all that. So we would say, yes, this one would be binomial. And so we could then say, well, what's the probability of getting a correct answer, and we get our sample size, and then we could figure out the probability that they get 4 questions right, or the probability that they get no questions right. We could figure those out using that binomial PDF. So this is binomial. All right, a teacher will roll a die until she gets a 5. Then she will record the number of rolls. Okay, so this is not. So why is this not binomial?
Because it's not a fixed number of observations.
That's right. So the very first thing we look for is, what is n? But we don't know here because she's rolling the die until she gets a 5. So if it's something where they're doing something until they get a success, that's going to be a different distribution. It's not binomial. So since we don't have this, then we know immediately it's not going to be binomial. All right, a group of 250 college volleyball players who are not related are randomly selected from across the country, and the number of left-handers in the group is recorded. Okay, this would be fine, right? We have 250 total. we do have a success or a failure, where we'd say, in this case, left-handed would be our success, because that's what we're counting. And then right-handed would be failure. Just in terms of our setup for the problem. So sometimes the success could actually be like a bad thing. I mean, if we're counting like the number of people that died from a certain disease, them dying might be a success in our trial, right? But it doesn't mean that's good, okay? It just means that's what we're counting. So that's just how it's set up. So like here, it doesn't mean left-handed people, are good and right-handed are not. It's just looking at we're counting left-handed, so that's our success. And then I put in here that they're non-related players, because I guess you could say, if several of those volleyball players were related, we might say, well, actually, then it's not independent, because some of them may be more likely to be left-handed if they're twins or if it, whatever, right? So we're just going to say that they're not related so that, we can be independent and all that stuff. So we would say, yes, this one is binomial. So we would look at overall, I think we did one the other day about left-handed. Oh, yeah, we had that contingency table. But we could look at, what's the probability of left-handed. We could put that in here and then figure out, what the probability is of getting a certain number of people to be left or right-handed. All right, read through the last one, see how you think about that one.
No, because those lights take more than 5 minutes to turn.
Right. That would be an interesting study to do, to have to do that. Now this one, even if we had, we could maybe have a sample size. I didn't put it on here. But we could look at, how many stoplights are on Scottsdale Road, right? So we can figure out how many there were. So it may have a sample size. That one would be okay. But the problem would be that we don't really have a success or failure, right? All it says is we're recording whether the lights were red, yellow, or green. So if we said we were going to count red as success and everything else as a failure, well, then it's possible we could maybe do this as binomial. So sometimes you just have to change the setup of your experiment to make it binomial. Some of them aren't going to work at all. But sometimes you can kind of adjust it to where, okay, well, let's say instead of just recording what color it is, I'm going to look at a certain color as a success and then everything else as a failure. So this one, as it is, would not be binomial. And I guess I'll also write on here that we would need to make sure we had a sample size. Because as it is right now, I don't really have anything written out on here.
So that 5 minute interval would not count. So
right.
They'd have to have a number of.
Yeah, either how many stoplights we're going to look at, or how many times we're going to look at a certain stoplight, something like that. All right, so any questions on those? Sometimes that's the hardest part, is just identifying, is it binomial or not? And then that might be what you'll see on some of your homework, just identifying like discrete, continuous variables, identifying if it's binomial or not. And of course, also binomial, they'll always be discrete. So that would be the other thing. I don't know if it specifically says that here, but it falls under the heading of discrete random variables. So we're talking about discrete variables here. So you want to have something that dealt with height or weight or time or any of those things. Okay, it would all be something you could count. Okay, so going back to this page again, let's go ahead and look at how we could use the formula, okay, to calculate something like this. And then we'll do some more examples and look at how the calculator can help us with that too. So you can do the formula by hand. I want to at least show you one of those. But more often you'll probably use the calculator option. But this one tells us we don't even know what this experiment is. All we know is that it's binomial. It has 4 trials. The probability of success is 0.12. And we want to know what's the probability we would get 1 success. Okay. So if we were working in chapter 5, and I said, well, we're going to do something 4 times, and we have a 12% chance that we get the outcome we want. What's the probability we'll get one of those outcomes? We would say, I don't know. I don't have enough information, right? But in this, because we know it's binomial, then really all we need to know is n, which is 4. There's 4 trials, right? And then p is 0.12. And that's all we need for the formula. And then we have here that we're trying to find the probability that x is equal to 1. All right, so then we would just start filling in the formula. So the first thing is we want to see, well, how many ways can that one success happen? So in this case, if there's 4 trials, the one success could happen on the first trial, the second, the third, or the fourth. So this is what this is telling us. We're doing the combinations, right? So from 4, we're choosing one success at a time. So that's what that first part is. Then we're taking our probability of success, which was 0.12, and we're raising it to the power of 1 because there's only one success that we're interested in. And then the last part, we're looking at the failures. Right, and we would say that's going to be 1 minus 0.12, or you could go ahead and put in 0.88, whatever, the probability of failure. Raised to the number of failures, which here would be 3, right, or 4 minus 1. Okay, and so we could put all that in the calculator. Remembering this part is combinations, so you do 4 NCR and 1, right, in the calculator. Then times 0.12, then times 0.88 to the third in the calculator. You should get so I can bring up the calculator here and show you. So we would do 4 math NCR 1. Oops, what should I do? There we go. And then times 0.12 times, I'll put it in this way. So it looks more like the formula, raised to the third power. Okay, and you could do it in steps if you wanted to do the combinations first, you know, and then find that, and then times 0.12 times whatever, if you wanted to make sure you aren't doing anything incorrect in there.
Do that one more time.
Like how to get to it?
Well, I went to math, I got 4 NCR and
Okay, and then you do 1, because that's what we're choosing, right? And then that will give you this. And then just multiply times all the other ones. Or do 4, choose 1, enter, and it'll give you 4, and then multiply times the other ones. All right, so this tells us that in this scenario, there's about a 33% chance that you would get one success out of those 4 trials if the probability of success is 12%. All right, so let's do some more examples. All right, so for this one, we're going to do a binomial distribution with 10 trials, and the probability of success is 0.3. The first one we want to do is we want to find probability that x is equal to 2. All right, so let's talk about how we could do this easier in the calculator instead of just plugging in the numbers. So there's something in the calculator that actually already has the PDF stored in the calculator. So the PDF is that formula we just typed in, and choose that thing. Okay. So the PDF, that formula is already stored in our calculator. So really all we have to do is go to the calculator and then plug in all the important variables. Okay, so we have to tell it how many trials do we have, what's our probability of success, and then what's our X value. Okay, so on this particular one, we have 10 trials, a 30% probability of success, and the X we want to know about here is 2. We want to know about 2 successes. So we're going to use this binomial PDF anytime we're trying to find the probability that X is equal to a certain number of successes. So it only works when you're finding X equal to something. Okay? And so you're going to find this. You're going to go to the second option. I'll show you this on the calculator in just a second. I'm just going to write it out here. You're going to go to the second option of the variables button, which is where we will find our distributions. Okay, and then you should see the binomial PDF. So we're going to go to second and variables right here under the down arrow. Okay, now these are all the different distributions that you could use for different random variables. Now we're obviously going to talk about the normal distribution in chapter 7. We'll also talk some about the t-distribution. But the rest of these we don't get to, but they're all, this is the chi-squared, there's the f, here's the binomial, then we have the Poisson, the geometric, lots of other distributions, right, that could be used. So almost every experiment will fall into one of those groups. So did everybody get to this screen? Okay, so second variables, we're getting to the distributions. And we want to go to binomial PDF. Okay, again, if you have a calculator that shows the prompts, then great. You'll just kind of type in the values. If you don't, then you would put yours in with commas. So we'll see that after we type these in. But our trials were 10, P is 0.3, and our X value is 2. Okay, and when we do case, it's basically just going to show it in those parentheses like this, right? So if you don't have the prompts, you have to remember the pattern. You put an N, P, and then X for the formula to work. Okay, and then you just push enter. And then that's our answer. So that's the same thing we would get if we used this formula up here, right? If we did 10 choose 2 times 0.3 to the second power and then 0.7 to the 8th power. Okay, you would get the same answer if you used the actual formula. But much faster to do it that way. All right? So any questions on getting that? Yeah. So you have this right here. Did you get to that? Okay. So then you just type in 10 and then comma, which is above the 7, and then 0.3 comma, and then 2, and then enter. Yeah. So you'll just have to type in order. Okay. Any other questions? All right. So that will be our answer for that one. Usually they have us do 4 decimal places for these for your homework, so I'll do 4 decimal places, so 0.2335. All right, so that would be one type of question where we're trying to find the probability that X is equal to a certain value, a certain number of successes. The other thing we might want to know is, what about the probability that X is less than or equal to 2? Okay, so we may not always want to know about exactly equal to a number, right? We may want to know about several numbers together. So there'd be 2 ways we could do this one. The first one would be we could calculate the probability of each of these and just add them together. We could say the probability of less than or equal to 2 is equal to 0 or 1 or 2. Right? We could add all those together. But that could take a little bit of time. Right? Just have to do the PDF for all of those. So luckily there's another option we can use, which is also in the calculator, and it is called the binomial CDF. Okay. You may have noticed it when you were going down the list. There was a binomial PDF, and then there's a binomial CDF. And the C here stands for cumulative, right? Which means you add them all up, right? Your cumulative grade point average or whatever, the whole thing together. And so what this is for is this is when you're trying to find the probability of x less than or equal to some value. So when I plug in a value, an x value into the CDF, it's going to look at the probability of that value and every value below. Okay, and of course they're all whole numbers. So if I put in 2, it's going to look at 2 and 1 and 0 and combine them. Okay, so this is a time saver because then I don't have to do it, multiple times. Do the PDF multiple times. But we're still going to put in the same values. It's still going to be NP and X. So for this one, it would still be the same thing. We're still going to put in 10, 0.3, and 2. But because we choose the CDF, we're going to get a different value because it's going to look at the probability of 2, 1, and 0. Okay, so let's go to the calculator again. We're going to do basically the same thing. Go to the distributions, but now we're going to go one more down to the CDF. And you can see that all these different ones have PDFs and CDFs. That's why they're all in here twice. So we want the CDF now. Okay, and then we're putting in the same values. So 10.3 and 2 again. So you can see, they look the same, except this is the CDF. And the CDF should always be bigger than the PDF because the CDF is adding up, multiple probabilities, right? So the probability that we would have 2 or less successes is 0.3828. So everybody get that to work? 0.38.
Upper, lower, sigma.
You must have chosen the normal.
It says normal.
Yeah, so go down and go all the way down to the binomial. You probably just clicked the wrong one in the list. It's still saying normal on that? Alright, so if you understand how to use the PDF and the CDF, that's what most of Chapter 6 is, okay? Because for calculating binomial probabilities, you're either actually using the formula, or you're using, the calculator option. So mainly what most of our examples are looking at is, okay, I've got these two options of using the PDF or the CDF. How am I going to use those in different ways? Okay, so we looked at finding the probability of x equal to a value, x less than or equal to a value. But of course there are other inequalities, we might want to know about. Greater than or equal to, right? What if we said, what's the probability there will be at least 6 successes? Okay, so sometimes it's written out, as our probability. Sometimes it's written out in words, right? But then we have to say, okay, well, what does at least mean as an inequality? So at least means greater than or equal to, right? So at least 6 successes means we have 6, 7, 8, 9, 10. Now this is greater than or equal to, so we can't just go to the CDF and use 6, right? Because that's going to give us 6 or less. But we want 6 or more. So we could do that by using the PDF, right? We could add 6, 7, 8, 9, 10 together. That takes way too long. So what we're going to do instead is we're going to think of the complement. So the complement of greater than or equal to 6 is less than or equal to 5. And we see that because, let's say, if we've got 0 through 10 for our possibilities, right, because we have 10 trials. So greater than or equal to 6 is here. And so the complement is the opposite of that. So we say, well, what's not included in that? And that would be everything over here. Right, so that would be the opposite. Right? So here's our greater than or equal to 6. And then the opposite is less than or equal to 5. And so why that's helpful, you say, well, now actually, I'm still looking at a lot of numbers here. Why is this helpful? Well, why is that helpful to look at x less than or equal to 5? Right, but why is this easier to calculate than this? Right, because this, less than or equal to, I can use the CDF, right? It's not that it's less numbers or anything. It's that our calculator is set up where we can use a PDF or a CDF. So we want to try to get everything in terms of either that PDF or the CDF. And then sometimes that involves using complements as well. So we'll do 1 minus the binomial CDF of 10, 0.3, and 5. Right, so you could put it all in there at once, or you could find the CDF and then subtract from 1. I think I have it written out, so let me actually do that one. So we're going to have 10.3 and 5. So we get 0.0473 would be our probability. So, not very likely for that to happen, for us to have at least 6 successes. And that's because our probability of success is 30%, right? So all your problems for the binomial should be able to be solved with the PDF, the CDF, or some combination of those along with the complement rule. And so that's why the complement rule is very handy here in Chapter 6, because we don't always have everything in terms of PDF or CDF, right? One other thing we could ask on this one, not having to do with probability, but what if it asked how many successes do we expect in 10 trials? So if we want to start to look at, was my experiment unusual or not, first we would say, well, how many successes did we expect to get in those 10 trials? So how would we find that? When we are looking at expect, we're thinking of our expected value for this, which is the mean, which for binomials is just n times p. Okay, so to find the expected value, how many successes we expect in this experiment, we would do n, which is 10, and p is 0.3. So we expect 3. Okay, so 3 successes is what we expect, which is why in C, that wasn't very likely to happen, that we would get 6 or more, right? Because we're only expecting 3. So, yeah, we might get 2, or we might get 4, or maybe 5, but the chance that we get 6, 7, 8, 9, or 10, is pretty unlikely. So that's why we see a low probability up there. All right, and then if we wanted to see, well, how unlikely would it be to get 8, then we could also calculate the standard deviation here and, do that stuff with the empirical rule or something to figure out how many standard deviations there is. Okay, so that's the gist of Chapter 6. The only thing left is just more examples. Okay, and so we'll work on those next week. Make sure to finish your Week 7 weekly review. It should just cover the end of Chapter 5. It doesn't have anything for Chapter 6 yet. Next week, the weekly review will have Chapter 6. On Monday, we will finish up these examples, any other questions you may have, and we'll talk about the test. And then Wednesday, we will take the test for Chapter 5 and 6. And then remember, over fall break, you're going to do your midterm at home on the computer, and then finish up all your homework for Chapter 5 and 6. Okay? Any questions?